For the opportunity to present some small recent result. So I have to apologize right away because I mean, even though it says almost periodic in other ergodic problems, it's actually not almost periodic, and it's also not ergodic, but it's somewhat motivated from an ergodic famous ergodic problem. So okay, so well, in general, I want to, so let me start a little bit more general than this model before I'm telling you about antitrees. So in general, I'm interested in considering random Schrödinger operators on graphs. And by graphs, I mean sort of discrete, edge-connected, locally finite, and countable infinite graphs. So okay, so discrete should be clear. Edge connected, okay, so for each two vertices you find a path along edges. Locally finite, each vertex has only finitely many neighbors. And okay, you should have countably many vertices. And on such graphs you have some graph or step distance, which is just the minimum number of steps you need to go along edges from x to y. Okay, and then in general I want to allow for some edge weights. So by the way, I would locally finite means I do not necessarily have a uniform upper bound on the number of neighbors. So however, when looking at adjacency operators, I actually like to have finite operators, so I don't need to worry too much about self-adjointness. So therefore I allow for some normalizing edge weights that should be real numbers whenever you have an edge from x to y, and a of xy is equal to a of yx. And if we don't have an edge, so if the graph distance is not 1, then we set this equal to 0. And I want these weights to be chosen in such a way that it defines a bounded operator on the L2 space of the vertices. And then the Anderson model on this graph with these weights is the following. So I have this adjacency operator, and I add a random IID potential. So the operator just looks like this, and I have this V of x IID potential. Typical normalizations is setting the expectation to 0 and then having some coupling constant okay, acting on the L2 space. Now I'm in particularly interested in spectral theory of such operators, and also particularly on dependence on some kind of growth rates and something that one might call dimension. So what is my concept of dimension? So let's say if I have my graph, I first assign some finite set, which you may call the roots of the graph. Then what I would call the nth shell, or you could also call it the nth sphere if you have just one root, is the finite set of vertices that have graph distance exactly n from the roots S0. Then by our assumptions, so we had edge connected and locally finite, all these SNs will be finite sets and they will not be empty because altogether I wanted to have a countably infinite graph. And so for each shell, I mean, we can take the number of vertices in the shell, correlated as n, and the graph will be actually the disjoint union of these shells. And then I have this following concept of dimension. So I say that starting from these roots S0, the growth rate of the graph is at least d-dimensional if it's if Sn is greater than some constant times n to the d minus 1 for some causative constant. At most d-dimensional if you have an upper bound like this. Okay, exactly d-dimensional if it's sandwiched in between. But even this is, for some of my results, actually not enough. I need some even better than that, and this is uniform d-dimensional growth rate, and that's that the limit of Sn divided by n to the d minus 1 exists. And why do I say starting from S0? So actually this concept here, when you have just some arbitrary graph, may very well depend on what your roots are. Okay, an infinite dimensional, well, okay, if this limit is infinity. And just as a remark, the lattice CD, no matter what roots you choose, will always have uniform d-dimensional growth. Okay. So let me very briefly talk a bit about the ergodic model that is typically considered. So when you take your graph to be CD and you take edges between nearest neighbors, then the graph distance is typically a difference of the one norm of the difference, and you take your edge weights equal to 1, and then you get this Anderson model on CD, and then results that are known are mostly in direction of localization. So if sort of your distribution is regular enough, which typically means some type of Hölder condition, then we know that we have localization, so poor point spectrum, and for large disorder, and that's spectral edges, and exponentially decaying eigenfunctions in dynamical localization. And already mentioned in the talk by Mira are these methods, multi-scale analysis, first by Fröhlich-Spencer and refined by Klein-Germinet, and fractional moment method introduced by Eisenman-Molchanov. Now in one dimension, what's typically known is that you have localization and exponentially decaying eigenfunctions, even for small disorder and even for Bernoulli potential. Okay, and now besides these results, there are quite a bunch of open conjectures. So one is that also for the Bernoulli potential in high dimension and last disorder, one should have localization. Now, as also mentioned in the talk by Constanza, in continuous models, the situation is actually better because of the unique continuation principle. One can handle Bernoulli potentials there, but in the lattice, it's still a problem, and the problem is to get a Wigner estimate to start the multi-scale analysis. Now, it's also expected that you have localization for small disorder in 2 dimensions, and it's expected that from 3 dimensions on, and at least small disorder, you should have some absolutely continuous spectrum, meaning some delocalization. And the phase diagram is supposed to look something like this. So you have some AC spectrum here and some localization and some Anderson transition. But as I said, I will not present some result about some ergodic problem here because simply speaking, this ergodic problem is way too hard for me. I look for easy problems, and I think it's fair enough to say after several decades of people trying and not really getting these results that they are quite too hard. So I was wondering, can one kind of find some family of graphs that are sort of nice, and maybe you can have all kind of dimensional growth rates, and that you can sort of handle more in an easier way. And in some ways, when you look to physics, there's always these ideas about some kind of mean field theories that seem to be better manageable. And so the idea was to look at graphs that kind of produce locally a mean field. And one of these graphs is the anti-tree with normalized edge weights. So how does this look like? So we take some sequence of positive integers, and we look at the following graph. So the sequences n will also correspond to the number of vertices in the nth shell, as I said before. And so the nth shell will have exactly Sn vertices. And now we take all connections between the nth and the Sn plus first shell. So here is I'm starting with one root, and then I take all connections to the next. I take all possible connections to here, and so on. And I have no further edges. Now, if I take this graph and I want to look in particular at some higher dimensional growth rates, so this polynomial growth in this set of vertices, then I get sort of a lot of edges, and I don't want to make the Laplacian, the adjacency operator, too big, so I have some normalizing weight, and it may look a little bit strange, but I hope you will will understand it better in a few minutes. So for the edges between Sn and Sn plus 1, I take this normalizing weight 1 over square root Sn times Sn plus 1. Okay, and this I call the anti-tree with normalized edge weights associated to this sequence. Actually, in some talk before, I had called this graph differently, but I was told by Matthias Keller that in some setting of stochastic incompleteness, such graphs have been considered by Wojciechowski and called antitrees. Okay. So now let's look a bit more precisely on how this Anderson model looks. So since I have these shells, it kind of makes sense to decompose the L2 space as a direct sum of these shells. Now the L2 space of these shells is of course isomorphic to C to the Sn, right? And so I decompose my vector into these vector groups psi n. And so the difference to strip models now is that the size of psi n depends on n. And then the model actually can be written like this, and there you see that it sort of has actually some nice, almost like one-dimensional kinetic structure. So, so we have these vectors phi n, they are in C to the Sn, and then when I take this operator, this Anderson model applied to psi and the nth component, then what I have to do is take this, okay, phi n minus 1 star psi n minus 1 plus phi n plus 1 star psi n plus 1. So this just means you have a column vector times a row vector. So this is just a physical scalar product that's antilinear in the first and linear in the second component. So these are numbers now, and then you multiply these by this vector phi n, and then, so this is the adjacency part, and then you have these this random potential. So how can you actually understand that this really corresponds to the anti-tree? Well, so if I would write this as a semi-infinite matrix, then what I would have is here I have this V0 and V1. So here I have the potentials. So these V's actually are diagonal, and these are the IID random variables. So these are the potentials on the shells, and these blocks actually, I mean, typically in my model now get bigger, right? And then here I have phi 0, phi 1 star, phi 1, phi 0 star, and so on. And when I take this, so this is basically 1 over square root S1, and then you have a column vector. No, you have a you have a column vector, and you have the other normalization as 0, and you have the row vector. So when you make the product, you get a matrix with only ones as entries, and that just says that you have all connections from here to here, and so on. So this is how this operator looks like. And so I actually haven't kind of seen really this type of, I would say, more generalized structure compared to Jacobi operators, but so if somebody in the audience can point me whether such things have been considered before, then I'm happy to also change the name for that, but for now I call this actually an operator with one propagating channel. The one propagating channel being defined by the sequence of the phi n's. Okay. Now let's we need some more assumptions. So let's say that the support of the potential. So this should be, this PV is the distribution of a single site potential is bounded, and we call V plus the maximum of the support and V minus the minimum. Whenever energy divided by lambda is not in the support, we define this harmonic average of E minus lambda V. So we take the inverse and take the expectation value with respect to this measure, and then from this expectation value we take the inverse again. And then I take the set I lambda, which is the set of energies that are so not inside here. So in this interval, when I have my coupling constant lambda, all my potentials will be inside this interval. So I want my energy not in there, and this harmonic average, the absolute value, be smaller than 2. And this will be the set of energies where we'll say something about. Now some small proposition. So first you may wonder of the spectrum as a set. Now now this model kind of includes the one-dimensional Anderson model just by setting all Sn's equal to 1. And there you know the spectrum is minus 2 plus lambda times the support of the measure, almost surely. Now this is still true as long as the sequence is bounded. If the sequence goes to infinity, then, I mean, it's not an ergodic problem. The spectrum actually will be random, but the essential spectrum will not be random, and will be given by, okay, all the energies not in the support where this harmonic average is smaller than, actually smaller equal than 2, should be a closed set, and union with lambda times the support of the measure, almost surely. And in particular, this set is in the essential spectrum, almost surely, and actually it's well, from these assumptions here, it's not so hard to derive that it will not be empty as long as lambda is smaller or equal to 2. And so now there's the theorem. So if the sum of Sn to the minus 1 is smaller than infinity, then the spectrum is almost surely purely absolutely continuous. And this is particularly the case when you have at least d-dimensional growth rate for some d bigger than 2, because then Sn will be something like n to the 1 plus epsilon, and 1 over n to the 1 plus epsilon is summable. For the singular part, I need some more assumptions, so I need uniform d-dimensional growth rate. So this limit should exist. And the distribution should actually be absolutely continuous. This is because I'm using Simon-Wolf criterion at the end. And then between 1 and 2, the spectrum, I mean, if t is between 1 and 2, so the growth rate something less than 2-dimensional, then the spectrum is almost surely pure point, and the eigenfunctions decay sub-exponentially along the shells with some non-random rate gamma and n to the 2 minus d. And you see when d goes equal to 2, then this goes to 0, and then actually this kind of becomes logarithmic. So when we take d equal to 2, you have formal solutions that decay like n to the minus beta, but now you know that this will only give an L2 vector if beta is greater than 1/2. So now we have two sets, one where we have almost purely singular continuous spectrum, and that's the set where this beta is smaller equal 1/2, and the rest in the lambda where we have almost purely pure point spectrum. So if we look now at the subclass of uniform d-dimensional growth rate, then there is a transition in some sense from going pure point to pure point plus singular continuous to going to absolutely continuous spectrum in that energy, in that interval, d lambda, where actually it's a disjoint union of two intervals. Okay. Now, very briefly about the proof method. So I already kind of said that in some sense it's a one-dimensional structure. So when you look at this equation and you look at the eigenvalue equation at an energy state, then you can sort of so you can sort of put this here with the inverse, right? And what you realize is you only have these scalar products, so these are numbers, so let's give these numbers a name, un, and then so we take this over here, and then we take phi n star, psi n is phi n star, this inverse phi n, so this is here, times un plus 1 plus un minus 1, and this you can write in transfer matrix form, where now in the transfer matrix what appears here is a Schur complement of this potential with respect to this vector phi n. And now when you take your energy to the real line, then actually the Schur complement will not always exist, but for the existence actually, so this inverse is more crucial than that inverse, because So this inverse may not exist, but as a Schur complement it may still exist, and then this is still fine. And then basically, so the key element is sort of this. When you look in this particular model, then what you have in this entry in the transfer matrix is this harmonic mean of these values E minus lambda V in the shell. Now in this energy region I lambda, all these had a definite sign, and so therefore the harmonic average of these random variables, the variance goes like 1 over Sn. Right, and this is sort of the main part, and one can treat after adapting techniques from the theory of one-dimensional Jacobi operators, one can treat this very similar to random decaying potentials in one dimension. Okay, and so I think so here it's just so what you need to do for the spectral theory is sort of go through the one-dimensional theory, and you know, and here you have there you have connections between Green's functions and transfer matrices. The difference here is that there's some part where you need to be careful because you have energies where not all transfer matrices are defined. But actually I took an energy interval where I stay away from them, so that's why everything is very fine. And then you sort of translate the arsenal of theorems about spectrum, like subordinacy theory and all kind of theorems that Simon last and Kisilev Simon last proved in the one-dimensional way. And once you've made sure that all theorems work more or less with some modifications, you can push the proof through. Okay. Yeah?
In your framework, can you, well, you define models with given volume growth, but can you simulate more some other geometric properties like Cheeker dimension from the other properties of the dimension, for example, isoprometric inequality?
Like.
Is there are there graphs in the analyzable class with the prescribed isoprometric dimension?
I don't. Yeah, So you mean where somehow the number of edges is in the number of neighbors is in the right?
So that you can't the boundary of a set of given size, the relation between the size of a boundary of a set and the size of the set is as on the dimension.
Yeah, I don't really know. Would be interesting to think about that.
Somehow the belief is that this could be the property which is.
Yeah, but I actually think that maybe in the discrete case but one should really look more at this type of. I mean, I think in the discrete case the property is somehow on how many random variables you have when you go out, right, in the shells. And I think in some sense you need to go to spherical coordinates, because at some point you want to maybe think of dynamic localization, right? And I mean that even in these three cases, right, where you have the first result about AC spectrum, when you make a radial symmetric potential, so when the number of potentials grows like n when you go out of random variables, you have localization. Right, so I think somehow this quantity is maybe more important, but yeah, I don't know. I mean,
another quantity which is believed to be related to the mechanism for Anderson transition is the recurrence or transience of random walk.
Yeah, I have actually looked at this, and I think there is. So unfortunately I haven't worked it out yet, but I think that this would also work here, because somehow, I mean, you have these so you can here sort of reduce it to a one-dimensional model to kind of some like birth and death process with probability to go forward and backward, and with this normalizing quantity, I mean, there is something. So it seems to me like here that the rates, when you take this adjacency operator or make it the Laplacian and think of it as the generator of a continuous time random walk with exponential clocks for waiting times and so on, that you get rates that are something like Sn plus 1 divided by Sn, or with some square root or so. And I've recently seen some criterion that if some sum with birth and difference of p and over q and is finite or infinite, that exactly then you have recurrence or not. And I actually have the feeling that it corresponds to this sum of Sn to the minus 1 being finite in this model. So it could there could be some relation, but I'm happy to work it out whether it fits exactly.
Well, I think crucial that you have complete connectivity from one layer to the next. I mean, this is somehow your results are very close to the geometric situation, but that aspect is artificial. So I was wondering whether you can.
Yes. The aspect is artificial, right? I mean, it makes a. So first of all, this was somehow the simplest model I could think of, and it sort of. I mean, the point is, it makes the connection from shell to shell rank 1, and this is kind of crucial, because this makes the Jacobi thing work. Now, to make it higher rank, I think, and make something similar mean field approach, one would first maybe have to think of random decaying potentials on a strip and see whether there is something similar, but I'm not sure if this has been done. I actually have not seen it. So, but once you do this, then you can have, group this a bit differently and maybe have rank k, but fix the rank, right? I mean, what would be interesting now to investigate is, of course, something when maybe the rank increases, right? But I mean, so the point is actually every discrete model you can sort of bring in this tri-diagonal form with growing blocks. This is always possible. But normally in CD, these blocks here are already full rank. And I think this is kind of complicated. And in some sense, in this way, CD is among the most complicated graphs, even though they look so nice somehow. And so I think one should maybe analyze first cases where the rank of these off-diagonals grows much slower than the size of these blocks in the middle or so. But yeah, no, I mean, so far I cannot do very much. I agree.
More comments, questions? Let's thank Christian.